Last time we have seen memory type, read-only memory, ROM, and then we said that predetermined data is stored in the ROM. You just read it, or the microprocessor, can read it. Here, we also started seeing how we can make a RAM, and in the RAM structure, we can write data to a memory cell and then read it later on. So there are two types of this, maybe static RAM and dynamic RAM. So we started seeing how we can write the data and store it in a memory cell. So we mentioned that which memory cell that we will be writing or reading is going to be determined by the address decoders. One is the row address decoder, the other one is column address decoder. So here we will be assuming that we have access to 1 bit. So if we want to make maybe 8 bits, so we will be forming 8 of this same structure. But that's a design consideration. Sometimes they make it so that 2 bits are stored, or maybe more. But here in the design, at least in the configuration, we will be trying to access to 1 bit. Let's say in here, we will be accessing. And how do we access that? We select, one of them 1. And then also we select, let's say this one is 1, so that we can read this data to the output. That's how it goes. So each memory cell is important. So this important, which stores the data 1 and 0. And the way that the memory is formed is to use this back-to-back. The basic idea is to use back-to-back inverters. These back-to-back inverters, as you know, if the stored data is 1, this will give you 0, and then this will give you 1. So it's like if you remember, we talked about this in the past. This is like a bistable multi-vibrator. The data which is stored is going to be settled here, either 1 or 0. So there are 2 stable states here. And then we can change and switch the data. In the past, we have seen that we can do that with SR flip-flops. But here, the data is going to be written from maybe a line. Okay, so this line is touching to this bit cell, or the upper bit cell, or this bit cell. Okay, each of them is bit cell. So how do we decide which one to access? We give a signal to here, select signal. So word line determines which one we will be accessing to. So there are 2 cases here. The connection is shown like this. So this signal is coming from output of this. So output of that is connected to here, or the output of this is connected here. So in fact, this looks like 2 back-to-back inverters. But if you want to see all the transistors, this is what we do. So here, the transistor sizes is preferred to be selected to be minimum size, so that a memory cell occupies a small area. But if you make those transistor sizes small, then changing any signal here, because this is a line, there are maybe thousands of bit cells are connected, so it forms a big capacitance. So you know, writing the data from inside to these capacitances is going to be difficult. Okay, so how do we determine, for example, if there is nothing here? Okay, so or both of them are 0. Let's say we store here 5 volt. Okay, that's, let's say 5 volt here, and then 0 volt is going to be across this one, right? So this 5 volt, you know, if you start turning this on and then short this here, how is it going to be sharing the voltage here? So this 0 volt is going to be not that much. Okay, so as you know, the final voltage, if you short this thing, is going to be the total charge is preserved. So this one plus maybe 0 times CV divided by CQCV, okay, and plus CV. So this is going to be very small. Okay, why? Because CQ is much smaller than CB. So this is going to be in maybe millivolt levels. Okay, so therefore, you know, reading the data, internal data out, we will be doing some tricks, you know, to be able to, you know, read that at the output. But the first thing is how maybe we can, you know, write or yeah, how do we write the data? So if we want to write the data, let me see, we will be, maybe first we'll be saying how we can read it. Okay, that's maybe more convenient right now. So here, again, like we have the bit line and then bit bar line. Okay, so this kind of differential output is useful for this device. And the circuit is like this, of course, same as this one. So if you want to you know, write things fast, you need to have large WL, but if you have large WL, then it occupies a lot of area, and we want to store a lot of data into small area. So therefore, you know, we select minimum size transistors typically. So in order to let's say read any data which is already in here, so let's assume that here there is you know, 5 volt. 5 volts across this capacitor, internal capacitor. We don't put any capacitor in there intentionally, but you know, there's already internal capacitance of this node. So this 5 volt is connected to the input of the next inverter. Okay, and then output of this inverter is going to be 0 volt. So that is connected to here, so that the 5 volt is going to be justified also. Okay, so this is like 0, 5 volt. So this is 5 volt. So this is going to be 0. So it supports itself and then keep the data, the stored data in there. So if you want to read the data out, you know, instead of putting both here and 0, we initially set this line and this line to external electronics or external part of the chip, sets this thing to 2.5 volt. I mean, there are different arrangements, but typically this is what we do. So then, if this is 2.5 volt in the CB, and then 5 volt in the other point, VQ, what is VQ? The voltage of Q and voltage of Q bar. So voltage of Q is going to be VDD, right? I mean, so this was VDD. So that's VDD. The other one is 0. So this is 0. Okay, so the data is stored like that. So when the word line, is selected, what happens is that, this becomes short and this becomes short. So therefore, a bit line voltage, bit final voltage is going to be, again, like, the total charge bit. Let me do this again, maybe nicely write it. V bit voltage is going to be the final voltage of V bit times CQ plus CB should be equal to V bit final, okay, V bit initial, which is like 2.5 volts times CB plus 5 volts times CQ, okay? So if we read this thing and then look at this one, the voltage at VB, I think there's a slight mistake here, yeah. So this should be VD divided by 2, and then this should be VD divided by 2. So the voltage at VB is going to be slightly increase. So the voltage here, VQ, is not going to be 5 volt anymore. So it will be with V bit final. Okay. And then what is that V bit final? V bit final is going to be equal to, 2.5 CB plus 5 times CQ divided by CQ plus CB. So it's going to be basically larger than 2.5 volt. Okay, so VB slightly increases after this turns on. So just maybe few, some millivolts. Okay, and while the other one, VB minus, it used to be V bit final bar, C is going to be equal to 2.5 times C bit plus 0 times CQ bar divided by CB plus CQ bar. So if you look at this, this will be slightly less than 2.5 volt because of charge sharing. So this will be slightly less, okay? And then this is going to be slightly larger. So the point here is that after this, charge sharing, if you wait enough, this Q4, remember this was 5, right? So this will be charging this node more because we shorted it, right? So this is active already. This is on. This is off. So this will, try to increase the voltage of this node, maybe to while it's on still, while this is on. VDD. Yeah. But we only have a short period of time. So this will start to increase. This will start to increase. But we don't have time for reading that. So if we wait enough, this will go back up to maybe 5 volts, okay, or maybe like 4 volts because of the voltage drop in the NMOS transistor. But the point here is that this 2.5 volts is going to be increased here slightly, decreased here slightly. So if we let we keep this enough long, and then if we also wait enough, then the voltage here in the bit line will reach to 5 volts or 4 volts maybe. And this will go down to 0. Why? Because this one is on. Okay, so this one is off. So, but this takes a lot of time. If we make the WR ratio of the transistor large, then it can go up large, quickly, and then go down quickly. But this is really, in fact, a time consuming thing. Therefore, we have some support electronics to make that faster. And then that support electronics is shown here, sense amplifier, okay? So the function of the sense amplifier is to understand which one is going up and which one is going down, and help us to maybe charge up the node that is going up, and the other one to help to discharge fast. We'll see the circuitry which makes that circuit, but that's the basic concept. So in summary, any stored data, let's say you have 5 volt here and then 0 volt here, is going to be read before everything else. CBN, they are both put this VDD divide by 2. This is convenient. Some people select maybe some other numbers, but this is a convenient number. And word line is activated, and then this thing start to charge, and then the voltage is going to be slightly larger than VDD divided by 2. Okay, and then helpers arrive. So in this concept here, the stored data will not be erased. Okay, so we call this thing non-destructive reading. Okay, so you can justify and question, why do we think that's going to be destroyed? It doesn't, it's not destroyed here, but in some topologies, we'll see that it will be destroyed. Okay, so that's why we say this is not destroyed and it's a good thing. So if you want to write something, new data to inside, then this is going to be maybe, you know, in a sense straightforward. So this is connected and this one is connected here. So let's say initially there is 5 volt here. Okay, so 5 volt is here, and again 0 volt is here. So they support each other. So this one is off, and this one is on, and then this one is off. This one is on. Okay. So let's say we want to write the opposite signal. Otherwise, I mean, writing the same signal is not fun. I mean, it's the same thing. But let's say we want to write here now, I mean, 0 volt here. So in order to set 0 into the memory line, we apply here 0 volt, and then we apply here 5 volt. Okay, how? With the external, I mean, there are all these, you know, elements and circuitry here. So with the help of that, we write that data. So once we write that data, you know, there's going to be a conflict, in fact. So for the bit line, this is going to be 0 volts, but this one is going to be on, and then this is 0 volts, right? I mean, so this is going to be 0 volt here. So so what happens? Is this going to burn or something? No, really. Here, the device itself, I mean, you know, on the contrary, there's going to be 5 volt here, and this one is going to be VDD. This one is going to be on. And then what happens? I mean, there's going to be conflict here, right? So we connect here. So, you know, typically internal devices are weak. So WR ratio is, they are small. So then there's going to be conflict, and then charge sharing, and then voltage sharing here. And eventually this device, the voltage here, is going to be going beyond 0 volts. So there's VDD here. This one is on. This one is on. They are both on, and therefore the voltage, which is like 5 volt here, is going to be you know, winning the struggle because that is a good, you know, large amount of voltage. So therefore the weak transistor will lose. So the voltage here will be going beyond 2.5 volt. And once it goes beyond 2.5 volt, this inverter output will switch. So similarly, on this side, there is 0 volt here, and then there's 5 volt here. Both of them are on. So this is also on. And then, you know, VDD, and here, this node goes beyond 2.5 volts. And then, you know, then remember, I mean, we were saying that this is like 2 inverters back to back. They are like bistable circuit. So with the help of this, we managed to throw the ball from one side to the other side. Okay, so state 1, maybe state 2. So it goes from one state to the other state, and then it will be stable. So the data is going to be, you know, switched. So what is the argument here? So this 5 volt is strong, and then this ground is strong in the bit line, so that at the end, CQ becomes this one, VCQ becomes 0, and the other one becomes VDD. Okay, so you manage to change the internal data. And then logic 0 will be stored. Okay, so this is the basic idea for reading and writing, and we will be I guess we will see in the future coming slides how the sense amplifier, sense amplifier, we'll talk about the sense amplifier later on. But you know, this is you know, static RAM. Okay, so some people call this thing 6 transistor memory cell. Why? Because there are 6 transistors in the memory cell. So another extreme is just to use 1 transistor in the memory cell. Okay, so so this is 1 transistor memory cell. So you know that 6 transistors occupy a lot of area, and then we want to fit many memory cells into a small area. So some people came up with this idea. They say, look, you know, why not just, you know, store this into maybe memory of a capacitor. Okay, so this capacitor maybe can be formed by a transistor also, you know. So they say, why not just, you know, connect this to ground and then use this as the capacitor, C gate to source capacitor. So the C gate to source capacitor is going to be CM. Or they do some other tricks to make that capacitance large, but in fact, still it's going to be much smaller than the CB capacitance. So this is memory capacitance. So if you want to write something, you know, so this occupies much less area than SRAM, of course. But it does not have, this is the good thing. The negative thing is that it does not have a latch. Okay, so so you store the data in here. Let's say you write 5 volt in here, and then if you write 5 volt, you turn this on, and then in fact this is going to be maybe 4 volt is going to be stored here because of the threshold voltage drop of the NMOS transistor. And then you know, you word line, you select and then write that 5 volt inside, and then it's going to be 4 volt, but it's going to be logic 1. Okay, logic 1. If that is in there, you know it's going to stay in there, but it will be not in there, stay in there forever because of the transistor. You know, this is the transistor, right? So you store it, let's say, the data in here in this capacitor, CM, but here there's a diode, okay? So a latch, but it can store the data in CM for a while. So what you need to do then is you know, read it. So we need to read the data and write it back, okay, periodically in a period that doesn't lose the data. I mean, the leakage doesn't. So maybe in few milliseconds. Okay. So this is a very you know, tough looking job, but it's worth it because if you think about the chip, the memory, you know, cells occupy like this much area. Okay. Memory cell area. And then you can, you know, put here circuitry. Okay, like, you know, maybe here circuitry for this refreshing. For refreshing. So I mean, it will take a little bit area, but think about that. If you can fit, you know, 1 transistor instead of 6 transistors into memory cell, the area, memory cell area, maybe 6 times efficiently used. Okay, 6 times efficient. So what, you know, if you spend a little bit extra area. So you know, if you want to read the data, so how can you read? Again, you know, let's say you put here, let's say 4 volt, okay, and the stored data is 4 volt. So we set here again this line to be 2.5 volt, and then the final voltage, the final voltage is going to be, I mean, 4 times Cm plus 2.5 times Cb divided by Cm plus Cb. So this is going to be slightly larger than 2.5 volt, okay? And then the external circuit considers it as logic 1 data, okay? And then there are some sense amplifiers also sense and increase this node to larger voltage. If the data was, if VCM was 0, then the final would be, you know, 0 times Cm plus 2.5 Cb divided by Cm plus Cb. So it's going to be something less than 2.5 volt, which is considered as logic 0 by the external circuit. When I say external circuits, the circuit within the chip, but outside of the memory cells. So this is how we write and read. Unfortunately, you know, when you read it, the data is lost. Okay. Note that the data in the cell or the charge in the cell is removed, so data in the cell is lost. But external circuitry know the data, and it is written back to the cell by the external circuit. Okay, so it you know writes it back. So how does it write back? Write operation. I mean, it's very simple. You know, in order to write it, I mean, first bit line to write 0 to the memory cell. Bit line is set to 0 volt. Then word line is selected. Selected means, you know, we apply VDD. Then it doesn't matter what is inside the CM, it will be set to that voltage. Okay. Then VCM becomes 0 volt. So logic 0 is stored. I mean, not too long, but you know, stored in the CM. To write 1 to the memory cell, bit line is set to 5 volt. Then the word line is selected like VDD as applied. Then VCM becomes, you know, about 4 volts. So the logic 1 is stored. Okay, so this is the general idea. I mean, there are 6 transistors memory cell, or 1 transistor memory cell, or there are 3 transistor memory cells. You know, in the past, all these were tried. But you know, when we look at this, structure, there are all these external circuitry, row decoders and other logic, external logic and other circuitry, to do all these functions. But one distinct block that we have here is the sense amplifier. You remember the cell here? The cell was back-to-back two inverters. So we said that here when the circuit becomes like for the reading operation, initially we set this 5 volt or 2.5 volt, this set to 2.5 volt, and in that line, this line is connected to many cells, right? There are a lot of cells here. So and then inside, minimum size transistors are used. However, we have like again two back-to-back inverters here with large WR ratio transistors, okay? And then, if this is 2.5, this is 2.5, so two back-to-back inverters here, two back-to-back inverters are going to be like here, and 2.5 volt, 2.5 volts, right? So this was like the ball. Remember, the ball is like sitting here. So that is a state, but it is unstable state. So if, let's say, one of the voltage starts to increase slightly, this goes to 2.6 volt, then this goes to, let's say, 2.4 volts, then this will be immediately roll to 2.8 volt, and then this will be immediately go to 2.2 volt, and then this will go to 3.5 volt, and then this will drop to 1.5 volt, and then this goes to 5, and then this goes to 0 volts. Okay, so the sense amplifier here, notices the trend here. So is this going up and this is going down? Then it puts the ball here, okay? So, and since this is the sense amplifier is, outside of the chip, and then you need only one line here, okay? Sense amplifier. So W, we can select WR ratios large to facilitate the decision, the voltage decision. Voltage target. Well, target value. Okay, so the sense amplifier, therefore, in the outside, just one line. So you might have many pixels here, but only, for each column, you have one sense amplifier. Okay, one sense amplifier. For each column. So therefore, it's going to be very efficient. So this slide shows maybe in a better way of explaining that, how we can do that. We apply 2.4 volts. So initially this bit line and bit bar line is settled to 2 point, and then make it equal. And in order to make sure that, they have equal voltage, we have one more extra transistor. So it balances out. So, you know, 2 back-to-back inverters, balanced out voltage, and then, you know, the sense amplifier notices if it goes slightly up, and then it helps you, you know, to go to VDD, that line. Okay, so this is the general concept here, and you know, the columns each have sense amplifiers here. Each column has its own sense amplifier. Okay, so that is the general idea of the RAM cells. I mean, there are cells, 6 transistor or 1 transistor, column decoders, and sense amplifiers. So the decoders are not complicated. I mean, you need to make the circuitry to select the decoders. So if the input signal is, let's say, 0, 0, 0, then only this one is going to be selected 1. The others are going to be all 0. Okay, but if you select this, the signal to be, let's say, 0, 0, 1, 0, 0, 1, then this is going to be 0, this is going to be 1, these are going to be 0. Okay, so you can, you know, decide to make this thing using maybe a NOR function. With the NOR function, W0 is going to be equal to A0 times A1 times A2 bar. Okay, so that's how you can write it. This one maybe A0 bar, A1, A2 total bar. You know, that's how you make the circuitry inside for this line and the other lines. Okay, so just maybe one more. This is let's say 1, 0, 0. Therefore, this will be 0, 0, 1, 0, 0, 0, 0, 0. Okay, so there are also you know, circuits, row address decoder, how it can be implemented. Like this is one way of implementation. Since it is NANDs and NORs, you know, you can make it like this. You can generate A0, A0 bar, A1, A1 bar, and then this is going to be very easy then to generate row 0, row 1, row 2, whatever. So the idea is very simple. So I'm trying to complete this and then finish for today, and next week we'll start to A to D converters. So what else is left here? Column, this was row address decoder. The column address decoder is also very straightforward. It's just logic design, and how this is done. I guess there's a typo here. 3 type, you know, 3 column decoder example, and I guess this is not really that critical, so we can skip that. You know, there are a lot of course, different type of implementation of memory. We have just seen, you know, the basic idea and just generally, you know, the concept of creating memory. And ROM and RAM, you know, that's what we have seen. I guess that's what we'll be stopping it. Okay. Is that okay?
Yes.
Yes.
Okay.
Hocam bu bitmiş PDF notlarını OptiClass'a yükleyebilir misiniz?
Tamam, yükleyeceğim bunları.
Teşekkür ederim.
Tamam. Başka? Bir şey var mıydı? Midterm 1 örneklerini yüklemiştik galiba. Midterm 2 örneklerini yüklemedik değil mi? Var mı onlar bilmiyorum ama.
Yok hocam, ben en son baktığımda yoktu.
Ya bizde var mı diye düşünüyorum da. Midterm 1 örneklerini bulmuş yüklemiştim. Midterm 2'yi de bulmaya çalışayım ben. Onları da yükleyeyim. Tamam mı? Bana bir iki taneniz şey atarsa iyi olur, hatırlatma. EE312 Midterm 2 Example Questions diye bir mesaj atın, olur mu?
Tamamdır hocam.